All right, well, we'll go ahead and get started. I already have too much time cut out, class. So we started on number theory. Last week, told you we were covering our most important theorem for number theory for this class, and we pretty much just focused on that one theorem. And what was the one theorem?
That was your divisibility one, the question one.
Yeah, it's one that tells you how to divide. It says pick any two integers you want, something like 116 and 24. And it's saying you can take any two integers and divide them by each other, and you will always get one and only one quotient and one and only one remainder.
Yeah.
And that's all it was. Pretty straightforward, but it was a handful to prove. That's often the way proofs in number theory go. It's kind of a nice field because usually what you're trying to prove is pretty intuitive, but then for how simple it sounds, the proof always just seems way more complicated than it should be. So, easy to understand what you're trying to prove, a lot harder to prove it. That's a common flavor for number theory proofs.
Wasn't it just A equals QB plus R?
Yeah.
Yeah, that's the way we would write it. If I'm saying A divided by B, if that's intuitively how I'm thinking about it, A divided by B, then I say there exists a unique Q in R such that A is equal to QB's, where Q is a quotient, plus R, our remainder, where R is bound by...
It's less than B, but greater than 0.
Yeah, it has to be greater than or equal to 0. Can be 0, that's fine. It means there's no remainder. But it has to be less than B. I can't say 10 goes into 27 once with a remainder of 17. 10 goes into 27 twice with a remainder of 7 is the correct answer.
Right.
So for any division problem, there's one and only one right answer, one and only one quotient, one and only one remainder. So that's what we did last week. Okay. Now, our next section is on our greatest common divisor, or I think the way that you've typically heard it is greatest common factor. The largest factor that goes into two numbers. You've probably done this a few times, so if I'm looking at 28 and 16, what is our greatest common factor? We're saying what is the biggest number that both these are divisible by?
4.
And in this case, it's 4. 4 goes into 28 7 times, and it goes into 16 4 times. So 4 is a large number that goes into both those numbers. So that would be its greatest common factor. We're going to call it its greatest common divisor. And I will be using the acronym GCD 1,000 times today. GCD, greatest common divisor. Okay? So that's all this whole next section is about, is greatest common divisor. That's it. So now let's get our exact definition for our greatest common divisor. If A, B, and D are all integers, such that D divides A and D divides B, then D is a common divisor of A and B. If D goes into A some integer number of times, and D goes into B some integer number of times, then D divides A and D divides B. What's a divisor of both these things?
2.
2. 2 is an example of a divisor of both these things, because 2 divides that, 2 divides that. 4 is the other one.
And 1.
1's another one.
That's it, right?
That's, well, we could start doing negatives if we wanted. But our greatest common divisor in this case is 4. But these are all common divisors.
Is there a least common divisor?
Is there going to be a least common divisor? Yeah, it will be the negative of your greatest common divisor.
Is that true for every? That's true for every?
Yep.
Fair? Okay.
Okay. So, these are examples of common divisors. That's what we mean by D here. So let me read it one more time. It should be perfectly clear. If A, B, and D are all integers, such that D divides A and D divides B, then D is a common divisor of A and B. If for any other common divisor E, D is greater than or equal to E, then D is the greatest common divisor. It's the greatest common divisor if it's greater than or equal to all the common divisors.
Right.
It's greater than or equal to all the common divisors, it must be the greatest common divisor. Make sense? Notice that 4 is greater than or equal to all the common divisors. So 4 is the greatest common divisor of those numbers. That's all we're saying there. So, if for any other common divisor E, D is greater than or equal to E, then D is the greatest common divisor. We use GCD for it, the GCD of A and B. We will use this notation, treating it like a function. We will say the GCD of A and B is D.
Okay.
That just means the greatest common divisor of those two numbers. Good so far? Okay. Now, what we're going to have to do over and over again is come up with the greatest common divisor for numbers. Now you just barely did it for whatever I had up there, 16 and 28, right? What if I gave you something like 1,296 and 513? How on earth would you come up, or maybe just use examples I have up here? Here we have 618 and 105. What's the greatest common divisor of both those things? How do you come up with that thing? Now I'll tell you the really, really, really stupid way to come up with it.
Try all the numbers.
Try all the numbers up to your smallest number.
Yeah, that'd be painful.
Check 1, check 2, check 3, check 4, check 5, all the way up to your largest number.
Smallest number.
All the way up to the smaller of the two numbers. Now if you're a little bit clever, you could say, well, it's only you only have to check up to the square root of the smaller of the two numbers, and then you would have found it by then. But,
Why is that the case?
well, actually, I guess it could be the number itself. Never mind, forget what I just said.
Okay.
Or couldn't you, for the little bit smarter, just count down instead of count up?
Maybe, but either way, that's going through a lot of numbers. Imagine if I were working with numbers on the order of 10 to the 100.
That is a big number.
Now, how many steps would I have to go through if I had two numbers, roughly 10 to the 100 size? How many steps would I have to go through to find their GCD? On the order of magnitude of 10 to the 100, if I'm going to check all the numbers up to one of the numbers.
Yeah, that's
To give you a sense, 10 to the 80 is roughly the number of atoms in the observable universe.
yeah, that's
So take all the atoms in the observable universe, double it again, and you've only increased it by a factor of 8. We're not close to this yet. We didn't even increase it by one factor of 10, doing all that doubling.
That's insane.
It's hard to even get intuition for how stupidly massive this is.
Do we have any other good way of finding out the
Right.
GCD of that?
So I'll give you an algorithm for coming up with the GCD. It's going to be called Euclid's algorithm. And it turns out that even with numbers this big, we could do it in approximately 7,000 steps.
Oh, that's pretty good.
It's ridiculously good compared to checking all the numbers all the way up to that.
Yeah.
Checking all the numbers all the way up to that, a supercomputer, the size of the observable universe, how long would it take it to figure out the answer?
Very long.
Whereas we, puny mortals, just using Euclid's algorithm, can do it in 7,000 measly steps.
Cool.
So, let's go through an algorithm for finding the GCD. Now, before we do the algorithm for finding the GCD, it's going to rely on one very important fact. Here's the important fact it relies upon. Pick A and B in the integers. So any two numbers. Let C be A mod B.
Okay.
So what is C in words?
The remainder.
It's a remainder. When you take A and you divide it by B, C is our remainder. Good so far? Then it turns out that the greatest common divisor of A and B is the exact same thing as the greatest common divisor of B and C.
Really?
Yeah, so when I'm trying to solve a problem, I don't want to find the GCD of these two numbers, so I'm going to take this number, divide it by that number, and get the remainder. And I'll use the remainder in those two numbers. And I'll repeat and repeat and repeat and repeat, getting smaller and smaller numbers. So, let's prove this fact, and then we'll go through an algorithm, give you some examples of actually calculating the GCD using this fact.
Okay.
So first let's prove this fact. So let A and B be any two positive integers. And C is going to be equal to A mod B.
Okay.
So it's a remainder.
Okay.
Now what do I know? I know from our last theorem that there exists a unique, don't have room for my explanation point, but there exists is also good enough. There exists a Q such that A is equal to QB plus our remainder. Remember, C is the remainder.
Yeah.
Q is our quotient, C is a remainder. So there has to be some Q such that A is equal to Q number of B's, quotient number of B's, plus C, where C is between 0 and B. Notice I required A and B to be positive integers so that C is always a positive number.
Okay.
Good so far? Okay, now I'm going to let D be the greatest common divisor, the GCD of A and B, and I'm going to let E be the greatest common divisor of B and C.
Okay.
And I'm going to prove that D and E are in fact the same number. So the GCD of A and B is the exact same thing as the GCD of B and C. That's going to be my approach from here on out.
Okay.
How am I going to prove this? I'm going to prove that D is less than or equal to E, and then I'm going to prove E is less than or equal to D. If they're both less than or equal to each other, they have to be equal to each other. If I'm less than or the same tall as you, and you're less than or the same tall as me, we have to be the same height. Make sense?
Yep.
So that's what we're going to prove. So, first off, I know D is the greatest common divisor of A and B, which means D is a common divisor of A and B.
Right.
Which means D divides A and D divides B.
Yep.
Which means that there has to be two integers, call them K1 and K2, such that A is equal to K1Ds and B is equal to K2Ds. Since it divides them, there has to be an integer I can multiply D by to get them.
Okay.
With me so far?
Yeah.
Okay. So now, what is C equal to? Looking at this equation, just move the QB to the other side. So C is equal to A minus QB. C is equal to A minus QB. And now we're going to do our substitution for A and B. A was this, B was this.
Okay.
So C is equal to A minus QB, which is equal to A minus QB.
Okay.
Follow that? And then notice, there's a D in both those. Factor out the D. And so C is equal to D times an integer.
Sick.
What does that mean?
That D divides C.
D divides C. So D divides C, that's what we just showed, and we already knew D divides B. So D is a common divisor of C and B. What is E by definition?
The greatest common divisor.
The greatest common divisor of B and C. I show D is a common divisor of B and C. E is the greatest common divisor of B and C. Ergo, D has to be less than or equal to E.
Yeah.
Because D is a common divisor of those numbers. E is the greatest common divisor.
Okay.
Good?
Yep.
Now, very similar argument going the other way. So this time, working with the E. So, back up here, what is E? It's the greatest common divisor of B and C, so it is a common divisor of B and C. So, E divides B and E divides C, which means that there has to exist two integers, M1 and M2, such that B is equal to M1 times E and C is equal to M2 times E. With me? Okay, so now I need to show that E is also a divisor of A. So what is A equal to? A is equal to QB plus C.
Okay.
A is equal to QB plus C. Factor the E out. And we see that A is equal to E times some integer. Or in other words, E divides A. So I started with the fact that E divides B and C, showed that implies E also divides A. So E is a common divisor of A and B. But D is the greatest common divisor of A and B. Therefore, E has to be less than or equal to D. So we had D is less than or equal to E. We had E is less than or equal to D. Therefore, E equals D. There's the proof. Okay, so now with that proof, let's use that fact to take you through something called Euclid's algorithm for finding the greatest common divisor of two numbers. And here's what your homework is going to be a lot like. Or on your test, it's going to be something like find the GCD of two numbers. You're going to need to know how to do this by hand. And in particular, you're going to need to know how to do the exact algorithm I'm about to take you through. Otherwise, there's going to be problems that come up next week that you're not going to know how to solve.
Okay.
So it turns out Euclid's algorithm has a second useful fact to it that's very useful for finding the multiplicative inverse of numbers in modular arithmetic. And we'll understand what that means next week. But I promise, very important, going to use it a lot.
Okay.
Okay, so let's go to Euclid's algorithm. Find the greatest common divisor of 689 and 234. Well, the greatest common divisor of 689 and 234 is going to be the greatest common divisor of 234 and whatever the remainder is when I take the quotient of these two numbers. So let's find the remainder using our theorem from last time. We're going to keep writing A is equal to QB plus R over and over again. So I'm dividing this by this, bigger by the smaller. With me so far? So how many times does 234 go into 689? It's going to go into it 2 times with a remainder of 221.
Yeah.
Now, according to this theorem, the greatest common divisor of 689 and 234 is also the greatest common divisor of 234 and 221. So now I can repeat the problem. So now I'm going to take 234 divided by 221. How many times does 221 go into 234?
Just once.
It only goes into it once with a remainder of 13.
Okay.
So now my greatest common divisor of those 2 numbers is also my greatest common divisor of those 2 numbers. So how many times does 13 go into 221? Well, it goes into it exactly 17 times, remainder of 0.
Okay.
Once you get your remainder of 0, then whatever this number was your GCD. In other words, taking you through all the logic here, we said that the GCD of 689 and 234 was equal to the GCD of 234 and 221, which was equal to the GCD of 221 and 13, which was equal to the GCD of 13 and 0. And once you have a 0 show up, it's always easy. What's the greatest common divisor of 13 and 0?
There is no common divisor, is there?
There is. It's 13. Can I find an integer such that when I multiply 13 by it, I get 0?
Yeah. Okay.
Yeah. What is it?
0.
0. So 13 divides 0. Every number divides 0.
Cool.
Every integer.
Yeah. Wait, not every number?
Every integer. Divisible. This is this is a relation on the integers.
Okay.
So it doesn't make sense to talk about, does pi divide 0? That's a bad question.
Yeah.
Because it's not an integer, and we only define it for the integers. But you have intuition for why, if you somehow extend the definition, it would.
Right.
Okay, so once you get a 0, then the other number always is a factor of 0. So what's the greatest common factor of 13 and 0? 13. So the GCD of these 2 numbers, it turns out, was 13. A few measly steps to figure that out rather than trying to plug and chug all the numbers up to 234. Would have been a nightmare.
Yeah.
Okay, so now let's have you guys do an example. You'll walk me through, tell me everything to write. Make sure you know how to do this for your homework.
Okay.
So we're finding the GCD of these 2 things.
Mm-hmm.
So what do I start out doing?
You're at 618 is equal to...
Yeah, write the quotient for it, using the divisibility theorem from last time. So 618 is equal to how many 105s?
5.
5 105s. 5 105s. With a remainder of, you're going to have to know how to calculate these by hand. So what's 5 times 105?
525.
That's 525. Maybe we'll just scribble that up here, 525. So when I'm taking the difference between those, what's the difference?
93.
75 plus 18. Right? 525, you need 75 to get to 600, and another 18 to get to 618. However you want to think about it. So, it comes out to 93.
Okay. And now you divide 105 by 93.
Now you divide 105 by 93. How many times does 93 go into 105?
Once.
Sorry, I want to put my parentheses always on the Q. Goes into it once, 193 plus
And now it's 93 divided by 12.
perfect. How many times does 12 go into 93?
7 times.
7 12s. What, 7 times 12?
84, sorry.
So 84, to get to 93, how many more do we need?
9.
9. Now what?
Now it's 12 divided by
12 is equal to how many 9s?
1.
1, 9 plus 3.
Yep.
And then finally 9 is equal to how many 3s?
3.
3 3s plus 0. Okay,
So 3 is your
I know that there comes a point where you could have kind of guessed what the answer was. Maybe looking here, you could have easily seen, oh, it's 3. Make sure you know how to finish the algorithm all the way to 0, because it's going to be very important for what we do next week.
Okay.
And some of what we even do this week. So there we go. There's using Euclid's algorithm for finding the greatest common divisor. You feel like that's something you could do on a homework?
Yeah.
Something you could do on a test? If I were to give you that exact problem on your test, you'd be singing, you're so happy, so easy. Okay. Alright, so now, what is one of the things that this formula is extremely useful for? What's the best way to say this? Over and over again, we are going to get these equations, some number x plus some number y, and we're going to want to find when it's equal to a particular number. So you're going to be seeing over and over again an ax plus by, and you're going to be looking for the x's and y's that give you a certain solution.
Isn't that like a line?
Ish.
I thought that was the point slope formula? Or no, that's the... I thought there was a name for that kind of...
It's going to be linear plotting. Keep in mind, these are integers.
Integers. Okay.
So it's not going to be some filled-in shape.
Right. Okay.
So just give you a feel for what this equation is going to be like for our class. Let's say that A is 30 and B is 24. Then, what is this going to be equal to for all different combinations of x's and y's? Sorry, I didn't mark which one's my x and which one's my y. So here's my x's here. Here's my y here. And for different values of x and y, here's the number that comes out.
Okay.
So if I were to plug in negative 3 30s minus 3 24s, it would come out to negative 162. Make sense?
Yep.
If I were to plug in 0 x's and 0 for my y, it would come out to 0. So you'll see that there are infinitely many solutions to this equation,
Yeah.
depending on what your x and your y are. As infinitely many outputs is probably a better way to say it. Here is an interesting fact. The smallest number that gets output by this equation will always be the greatest common divisor of A and B.
Well, wouldn't that just be 0?
No. 30 and 24. So I picked numbers that you could easily reason about. 30 and 24. What's their greatest common divisor? 6. 6 is their greatest common divisor. Notice that 6 is the smallest positive number that shows up in this table. And it turns out it occurs when x is 1 and when y is negative 1.
That's cool. So can you find your x and y's using the greatest common divisor?
Well, so the solution that we are going to be interested in is the solution that gives us the greatest common divisor. So the problem is going to be over and over again, find the x and y such that this outputs the greatest common divisor between A and B. In this concrete case, looking at the table, it would have been x1, y, negative 1.
Yeah.
Unbelievable. That's so cool. I wish I could get that in my head. You're missing a lot of kids.
Just 2. I always have a small class.
Oh, okay.
We're missing Ruth Hammond
And Olivia.
and Olivia Timpson.
Thank you very much.
Very welcome.
Okay. Thank you.
Yep.
Have the best day ever.
Okay, so first off, I need to prove that the smallest positive number that comes out on this table will in fact be the GCD. And then it will be a regular problem that we solve. Find the x's and y's that makes ax plus by equal to its GCD. But first I need to prove the fact that I just told you, that the smallest positive number on this table, if I were to test every possible combination of x and y, the smallest positive number would be the GCD. So that's what we're going to prove next.
Is this symposium thing for physics or discrete math?
Discrete math. Yeah, sorry, I forgot to tell you guys about that last week. So short notice, I sent you an email what the requirements are.
Just pulled up on my data as a notification.
So have fun with that.
Okay.
We will, don't you worry.
We'll talk about it some after lecture.
Okay.
Okay.
Fucking history.
Yeah, that's what they want. They keep pushing the limits of these proof things. Okay. Anyways, so now we're going to prove this fact. I'm going to prove that if you would write out this table, given any a and b, if you were to write out this table, the smallest positive integer would be the greatest common divisor of a and b. Or in other words, I need to prove that there's always an x and y you can plug in, such that this equation evaluates to its greatest common divisor. That's what we're proving. Okay. I told you these proofs, always pretty easy to understand. Gets hairy in the details. So, let's get some hairy details. So, let a and b be integers such that a is not 0 or b is not 0. At least one of them is not 0. Why do we need at least one of them not to be 0? What's the greatest common divisor of 0 and 0? Yeah, bad question. There isn't one.
There's not one?
No,
Oh,
because any number divides both of them. So we need at least one of them to not be 0, otherwise this all breaks down.
right.
Okay, so let a and b be integers such that a is not 0 or b is not 0. Then the smallest positive integer that I can get from ax plus by, so pick an x and y to make this the smallest positive integer possible, it will always be the greatest common divisor of a and b. That's what I'm proving.
Okay.
Good so far?
Yeah.
Alright, let's set it up. Let a and b be integers such that either a is not 0 or b is not 0. Most likely they're both not 0, but at least one of them is for sure not 0. And now I'm going to let d be the set of all the numbers that show up in this table.
Okay.
So d is all the ax plus by's you could possibly get for every possible combination of x and y. With one limitation. We're only going to take the positive numbers.
One.
Why? Because we know that the answer we're looking for, what are we trying to prove? I'm trying to prove the smallest positive number that this outputs is the greatest common divisor.
Okay.
So already I know that I don't care about the negative answers. So throw those away right out the door. So d is equal to all the solutions you can get for plugging in any x and y as long as that number comes out a positive number. And so notice by definition d is a subset of the natural numbers.
So we can use the well order method.
Almost. What's the one more thing we need to use the well ordering principle?
You need to show that like our base case, so that's not 0. Or-
Yeah, you've got the right idea. We need to show d is not empty.
Yeah, yeah, sorry.
Every non-empty set of natural numbers has a least element. So we need to prove d is not empty.
Isn't that just
So I just need to find one thing in there.
right?
Well, notice that if I plug in a for x and b for y, then what do I get? A times a plus b times b. What's a number squared? Positive. What's a number squared? Positive or 0. But since they can't both be 0, this is a positive number.
Right.
And so this number will always be one of the things that shows up somewhere in your table. And it will be a positive number. Because they're both just multiplied by themselves. So the only point of saying that is that d is not theta.
It's not empty.
D is not the empty set. Okay, so now I know that D is some set of natural numbers, and I know that D is not empty. So by the well ordering principle, D must have some least element, call it little d. The remainder of the proof will be to show that little d is in fact the greatest common divisor of A and B.
Okay. That seems weird. Okay.
Okay, so first, I'm going to show that whatever that D is, does in fact divide A.
Okay.
And then I'll show that it does in fact divide B, so it is at least a common divisor.
Okay.
That's our next step here. So, to show that D divides A, assume by way of contradiction that D does not divide A. Good so far? Okay. Now, when I take A and I divide it by D, I'm guaranteed to get a Q and an R, such that A is equal to QD plus R, where R is between 0 and D.
Okay.
Just using the theorem we used last time. I'm basically taking A and dividing it by whatever that D is. Since I'm assuming that D does not divide A, then that remainder has to be
Positive or
greater than 0. So it can't be equal to 0. Notice whatever that R is has to be greater than 0.
You're right.
Good so far? And notice that R is also less than D.
Okay.
The remainder of this proof is going to be showing that R is inside this set big D.
Okay.
Little d was the smallest thing in big D. R is even smaller and it's in big D. Contradiction. That's going to be the contradiction we derive from here. With me? So, showing R is in this set. Well, what is this set? It's a set of everything that's A times some integer plus B times some integer, where the result came out positive.
Yeah.
What is R equal to from this equation? Just move the Q and the D over there. R is equal to A minus Q times D. Now, since D comes out of here,
Yeah.
D is A times some number plus B times some number.
Yeah.
So then R is equal to A minus Q times D. I'm just going to distribute the negative Q inside. So then R is equal to A minus AQX, just try and get in alphabetical order, minus BQY.
Okay.
Factor the A out of here, and I get A times something plus B times something. So R is of the form A times an integer, who cares what it is, plus B times an integer, who cares what it is. So,
It's in D.
So it's in D. D is the set of everything you could possibly make where it's A times an integer plus B times some integer. Here's one example. A times an integer plus B times one integer. So R is in D so long as it's greater than 0. But it is greater than 0. So then R is in D. But R is less than little d.
Right.
Little d was the smallest thing in big D. R is in big D and it's less than little d. Contradiction. Therefore D divides A.
And D divides B less than 1.
And D divides B, doing the exact same thinking but now with B. So I'm not going to bother doing that part of the proof. It's just a repeat for the exact same thing. Good?
Yep.
So far we've shown that D is a common divisor of A and B.
Okay.
What am I trying to show D is?
I'm trying to show that it's the greatest common divisor.
It's the greatest common divisor. So far I've just shown it is a common divisor. I need to show it's the greatest common divisor. How do I show it's the greatest common divisor? I need to pick any other common divisor out there and show it's less than or equal to D. And that would mean that D is the greatest common divisor. So now let E be any other common divisor. Potentially the same as D, potentially different. E is any common divisor you can think of for A and B. So from here on out, I'm showing E is less than or equal to D. That's the next piece, and then we're done.
Okay.
So let E be any other common divisor of A and B. What does it mean for E to be a common divisor of A and B?
E divides A,
E divides A, and E divides B. That's all it means.
Is it given that two numbers have a common divisor? I know, but how can you say let E be the common divisor of A and B? How do you
Let it be any common divisor of A and B.
How do we know that every A and B has a common divisor?
Well, one.
One. Oh. Fair enough.
So there's an example. But we've already found a common divisor, namely D. D is for sure, up to this point, a common divisor. So maybe this one only has one common divisor. Maybe it has more than one. There's always going to be more than one, because you can always have, at the very least, one and negative one. But, anyways, let E be any other common divisor, which means that E divides A and E divides B. Now, this is a homework problem that you guys did a while ago. But if E divides two numbers, then E divides any linear combination of those two numbers. Okay. So, E divides any linear combination of those two numbers. D is a linear combination of those two numbers. So then E divides D. And since D is greater than 0, E has to be less than or equal to D. Why does that follow? If I know that E, can't scribble right there, going off the board. If I know that E divides D, and I know that D is a positive number, E can never be bigger than D. I can never have something like 50 divides 10. I can't have 50 divides a smaller positive number than itself.
Right.
50 can only divide numbers that are, if it's a positive number, at least 50 or bigger. So, since E divides D, E can be at most as big as D, since D is a positive number. Why does it matter that D is a positive number? Notice that 50 can very easily divide negative 50.
The negative 50 is
And negative 50 in this case would be smaller than 50. So that's why it's important that D was a positive number.
Yeah.
So since E divides D, and since D is positive, E has to be less than or equal to D. And there we go. Therefore, D is the greatest common divisor. So big picture, what did we do? We set up this set of integers, set up this set of natural numbers, picked its smallest element, showed that its smallest element was a common divisor of A and B, and then showed that any other common divisor of A and B was less than or equal to D. So D was the greatest common divisor of A and B. That's big picture everything we did. Good? Okay. So there we go. That one is our second most important theorem for number theory for this class.
Okay.
The fact that you can find x's and y's to plug into ax plus by such that it spits out its GCD. And that the GCD will always be the smallest positive number. Good so far? Okay. So now I'm going to introduce you to an algorithm called extended Euclids. So this is going to be just like what we already did for finding the GCD. But there's going to be a second part to it. So here's the type of question you're now going to be asked. Find x and y such that 689x plus 234y is equal to their GCD, namely 13. We already showed that 13 was their GCD over here. So notice I'm using the exact same numbers.
Okay.
So my job is to find the x and y that make this equal to the GCD of those two numbers. This is what you're going to be required to do. And it's very similar to just finding the GCD and then doing some substitution. So you're going to notice everything I do in this left column is identical to what we had over here. And it's only the right column that changes anything. So, how do we start with? I'm going to do 689 divided by 234. 689 is 2, 234 is with the remainder of 221.
Yeah.
Now, I do a vertical line on this side. I rewrite this equation in terms of the remainder. The remainder, 221, is equal to 1, 689, and negative 2, 234s. You'll see why we did that here in a second.
Okay.
Now, continue the same way we know and love. Now I'm dividing those two numbers. 234 is 1, 221 with a remainder of 13. Solve for the remainder over here. Once again, now I'm doing the division of those two numbers. 221 is 17 13s plus 0. Don't need to solve for the remainder once you get to 0.
Yeah.
You with me? Okay, so now, looking at this equation, notice that this tells me what my GCD is in terms of the numbers 234 and 221.
Yeah.
I need it in terms of 689 and 234.
Okay.
So I start with whatever my last remainder equation was over here. Here it is. And now I'm just going to substitute out my 221 with whatever my substitution is there.
Okay.
So here's my remainder. 13 is equal to this thing. I'm going to substitute out the 221. What was 221? It was 1, 689, and negative 2, 234s.
Yeah.
Distribute. How many 234s do I have? I have 1 here, and then negative 1 times negative 2 is
Negative 2.
2. So 1 plus 2 is
3.
So I have a total of 3 234s, and I still have, or now I have negative 1 689s. That's what 13 is equal to. So 13 is equal to 3 234s and negative 1 689s. That gives me my x and my y.
Cool.
So let's go through the process now, but with different numbers, ones that we haven't done yet today.
Wait, how do you know which one was x, which one was y? Why is y not negative 1?
X is whatever one's correlated with 689.
Okay.
Y is whichever one was correlated with 234. So that was given to us in the problem. And as a matter of convention, you'll notice out in the homework problems they give you, they typically do the x associated with the bigger number and the y associated with the smaller.
Okay.
But if you flip it, doesn't change anything.
Yeah.
Just like that. Okay, so now let's do it for 431 and 29. Good? Okay, so first we divide it. 431 is equal to how many 29s are there?
There's a few.
Is it going to be 13 or is it going to be... It's just got to be 13, right? Or does it get all the way to 14? Let's see. What's 13 times 29?
200.
We're going to have 290 if we do the 10. What's 3 times 29? 3 less than 90 if you want to think about it that way. What did you say?
87.
87. When we add those together, what do we get?
We get 377.
377. Let's see. So I was off by a bit. Let's see. We can do 2 more 29s, right? Or can we only do 1 more? If we did 1 more 29, so we made it 14. Adding 29 to this gets us what?
390 or 300.
It's gonna be
400 and
406.
406. So our remainder is going to be 25. Okay.
Sorry.
So it's equal to 14 29s plus 25. On the other side of this vertical line, solve for the remainder. 25 is equal to -1, 431 plus minus 14 29s.
You just minus that. Right?
Well, that's just what 25 equals.
Yeah.
Okay, now let's repeat our step over here doing Euclid's the way we know enough. Now we're doing 29 and 5. Or 29 and 25. 29 is equal to
125.
125 plus 4. Over here, we write 4 is equal to 129 plus -1 4s. Or sorry, -1 25s.
Yeah.
Good? Okay, next, we're doing 25 and 4. 25 is equal to how many 4s?
5? No, sorry, 6.
6 4s plus
1.
1. And 1 then is equal to 125 plus -6 4s. Now I can do the last step here, but this step's kind of redundant. Usually you can see when you're done, but I can say 4 is equal to 4 1s plus 0. Or in other words, my GCD of these two numbers is
4.
no.
Oh, it's 1.
What?
Sorry.
So the biggest number that goes into both those turned out to be 1. Turns out, most of the times that we're solving these equations, we're going to care about the cases where we know it's going to come out 1.
Really?
Yeah.
Interesting.
But anyways, so there we go. We found the GCD. So now what is the x and y that makes this equal to 1? How many 431s and how many 29s do I need to make this equal to 1? And so I need to write 1 in terms of 29s and 431s. Now, I always start with this equation. 1 is equal to how many 25s? 125 and -6 4s. That's writing it in terms of 4s and 25s. Now, just go up the table now doing your substitutions. So now I'm going to do the substitution. Replace my 4s with 29s and 25s. Notice that the two numbers here, one of them should always be the same as one that you already have. And so basically by doing the substitution, I'm getting rid of my 4s and adding 29s.
Okay.
And then going from here to here, I'll be getting rid of my 25s and adding 431s. And then I'll ultimately have it in terms of 431s and 29s.
Okay.
That's the idea. Good? Okay, so this is equal to, we're doing the substitution of the 4. So this is equal to 125 plus -6 4s. And 4 is equal to 129 plus -125. Right?
Yeah.
Okay, so now this is equal to, count up how many 25s I have. I have 1 here, and -6 times -1 is 6. So 1 plus 6 is equal to, how many 25s do I have? 7 25s. And then how many 29s do I have?
-6.
Plus -6 29s. So if my numbers were 25 and 29, then here's how many of each I would need to get exactly 1. But I'm not supposed to figure it out with 25s and 29s. I'm supposed to figure it out with 29s and 431s. So now, do our next substitution. We did this one, now do this one.
Yeah.
Replace our 25s with that. So this is equal to, I keep writing so big, let's see, this was plus negative 6, 24s, right?
No.
Or 29s, I mean, right?
Very nice.
Okay, so now this is equal to, we're replacing our 25s. So we have 7 for 25. 25 is 1, 431, plus negative 14, 29s. So 7 25s, do my substitution for 25 there, plus negative 6, 29s, right? So now, how many 431s do I have?
7.
7. So I have 7 431s. And how many 29s do I have?
Negative.
Negative 14 times 7,
Oh.
right?
Yeah.
So what's that going to be?
98. Negative
98 minus 6.
Negative 102. Or no. 104.
Okay, I lost track of it in my head. 7 times negative 14 is 98, right?
Yeah, minus 6.
Minus 6, 104.
Minus 104. Yeah.
Okay, so this is equal to minus 104, 29s. And there we go. That's the x and the y you would have to use to solve that.
So, okay, so y is negative 104. Okay.
Make sense?
Yep.
That's what you're going to have to do.
Okay.
On your homework and on your test, you're going to have to be able to do these by hand.
That's bad.
And that whole algorithm, that is called extended Euclids. Okay. Now you'll notice in this case, 439 and 29, or 431 and 29,
Yeah.
what was our greatest common divisor?
1.
1. 1 was the biggest number that went to both of them. So we say that if the greatest common divisor of two numbers is equal to 1, then we call those numbers relatively prime. What's your intuitive way of saying what a prime number is?
It's not divisible.
It's only divisible by 0.
It's only divisible by 1 in itself.
Yeah.
Those are it's only positive divisors.
Mm-hmm.
So we're going to call two numbers relatively prime if their greatest common divisor is 1.
Which makes sense.
Which makes sense. Notice that a prime number with any other number, any number in a prime number will always be relatively prime. Unless it's a multiple of that prime number. Okay, so in this case, 431 and 29 were relatively prime. But you don't have to have two prime numbers for them to be relatively prime. For example, let's look at 10 and 7.
Yeah.
What's their greatest common divisor?
1.
1. So they would be relatively prime. Or 16 and 25. The greatest common divisor, 1, so they're relatively prime, even though neither of those numbers is prime. Good?
Are any like sequential numbers relatively prime?
Like 10 and 11?
Or 9 and 10 or whatever?
Yeah.
They all are.
Oh, is it the case that they're always relatively prime when you have two sequential numbers? And my gut says yes. Because in order for them to have a common divisor, they would have to be some multiple of that divisor apart. If they're only one apart, then they're always going to be relatively prime.
That makes sense.
So I'm 98% sure, but could be not thinking about right. Obvious counterexample being 0 and 1, but...
Besides.
Oh wait, no, the greatest common divisor is still 1.
Oh, yeah.
So in that case, it still works. I don't know, there's probably something we're missing, but seems close to true if it's not true. Okay, anyways, that's what it means for two numbers to be relatively prime. The greatest common divisor is 1. Alright, simple corollary that we're going to prove now. For any two integers, A and B are relatively prime if and only if we can find some x and y such that ax plus by equals to 1.
Isn't that the
It's almost exactly what we just proved, just using the definition of relatively prime. So I didn't bother even proving this, we can just basically say it.
Okay.
If I know that there exists two integers, x and y, such that this is true, then 1 has to be their GCD, and so they're relatively prime.
Right.
And if they're relatively prime, 1 has to be their GCD, and so there has to exist integers that make that true. So didn't bother writing it out since it would just be almost nothing.
Right.
One that's also really simple, but I thought it merited writing a couple lines. So let D be the GCD of A and B. If E is another common divisor of A and B, then E is also a common divisor of D.
Okay.
Good? So let's quickly prove that. So remember what my let says here. Let D be the greatest common divisor of A and B. Since D is the greatest common divisor of A and B, then there has to exist x and y such that ax plus by equals D.
Yep.
So then, if E divides A and E divides B, then obviously E divides some linear combination of A and B, which means E divides D.
Yeah.
Good?
Mm-hmm.
Okay. So there we go. That's the end for greatest common divisor. Now we're going to shift gears and switch to what is called modular arithmetic. What is modular arithmetic? We're not going to do this whole section this time. I just want to kind of dip your toes into it to get you comfortable with the symbols. So this will be a lot easier than everything we did prior to this, with the exception of like one proof. But what is modular arithmetic? So first off, what is arithmetic?
Operations on numbers.
It's just doing plus, subtraction, multiplication, and division.
No exponents? Is that not included?
No. That's when you're getting into, well, you can think about that as multiplication if you want to think about it that way. Depending on how you do it. But there's our basic arithmetic, our basic operators. Plus, subtraction, multiplication, and division.
Yeah.
Now, your mean teachers all through school made you do arithmetic on these sets of numbers that have infinitely numbers in them. An infinite number of numbers in them, right? Like on all the integers. And so what modular arithmetic is we're going to do plus, subtraction, multiplication, and division, but we're going to do it on very small sets of numbers. Just like using like 5 numbers or 10 numbers. Just a few numbers. So really limiting our modular arithmetic. An example of where you already use modular arithmetic all the time is it's very similar to what you do when you're looking at a clock. If I tell you it's 10 o'clock, then in 4 hours, what time is it going to be? 2 o'clock. I take 10, I add 4 hours, and it somehow got me to 2? How does that make any sense? Well, we're kind of just adding, but we only have the 12 numbers we have around the clock when we're adding. We're going to do a very similar thing now, but rather than just doing the numbers 1 through 12, first off, we're always going to start with 0 rather than 1. It's very weird on our clocks that we use a 12 instead of 0. Right? What's the first hour of the day?
12.
12 instead of 0. So it's a lot like a clock if you just imagine a 0 instead of a 12. Then now what your clock is doing with your hours, it's basically modular arithmetic.
Okay.
And that's exactly how your minutes work. If your minute hand is currently at 48, then in 15 minutes, what's it going to be pointing at?
3.
Huh? 48 plus 15. Not 45 plus 15, that gets you to 60. 48 plus 15 gets you to
3.
just 3.
3.
Oh, did you say that?
Yeah.
Sorry. Okay. No wonder you're looking at me weird. Okay. Yeah. So the way you already do it with your minutes count 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, all the way up to 59, and then 0 again.
Or like military standard where you go 0, 0.
Or military time does it the same way, but the way we do our times and kind of the way months used to be done. Months initially were 12 months of 30 days. So it was the first day of the month, and the second, and the third, all the way up to the 30th day of the month, and then the next day is back to the first day of the month.
Right.
Cyclic like that. So you've already had intuition for modular arithmetic. That's exactly the type of thing we're going to be doing. So here's how we're going to define our sets. Z sub n is going to be the set of the first n natural numbers. That's what it's going to be shorthand for.
Okay.
So Z sub 10 is 0, 1, 2, 3, 4, 5, 6, 7, all the way up to 9. The first 10 natural numbers is 0 through 9. Make sense? Okay. So let n now be any positive integer. So what's the smallest n can possibly be? 1. And let a and b in Z sub n.
Okay.
So what is the smallest a and b can be?
0.
They can be 0, and they can also be 1, for sure. Z sub 1
guarantees that. Well, how do we know that A and B are both 0?
Oh, they can both be, let's see, I think I even said this wrong. I think n has to be greater than 1. So our requirement here is n is greater than 1, not just positive.
Okay.
So that our set has at least the numbers 0 and 1 in it, maybe more.
Okay.
But always for sure have 0 and 1. Okay. Here is how we're going to define our arithmetic. A, this is called modular addition. To remind us that we're not doing the plus on the regular integers that you know and love, I'm going to put a circle around it for a plus b. And what is this going to be? It's going to be a plus b mod whatever that n is. And a times b is just going to be a times b mod whatever that n is. You already do this when you think about time. So let's work through some examples, help get you comfortable with it. So let's look at z sub 10. What is that? It's all the numbers 0 through 9.
Yep.
So there's the set we're talking about. We have these two operations now defined on a set, plus and times. So question, in this set, what is 5 plus 5?
10 mod 10 is 1. Or 0. What?
So let's be a bit pedantic for the first one. 3, 4, 5, 6, 7, 8, 9. Okay, there it is written out. Start at 5, add 5 more. 1, 2, 3, 4, 5 takes you around to 0.
Oh,
Okay, it wraps around same way your time does.
what the heck?
So 5 plus 5 is 10. Now mod it by whatever the 10 is. Get you back to 0. Alright, what's 5 plus 8?
3.
Well, 5 plus 8 is 13 mod 10. What's the remainder when you divide by 10? It's 3. Or in other words, if you start at 5 and counted 8 more, you get 1, 2, 3, 4, 5, 6, 7, 8. 5 plus 8, 13, or 3 when we mod it.
I see the shit.
Cool.
What's 2 plus 2?
4.
That's very impressive. You guys can do 2 plus 2.
Okay.
Okay, let's get a bit trickier with it. What's 9 plus 19?
8.
What's 9 plus 19? I'll give you a hint. The answer is not 8.
It's not?
No, it is not 8. Not tricking you this time. I promise the answer is not 8.
Well, you add 10, you get back to 9. Then
Extra
back
credit if you can tell me what the answer is in the next 5 seconds.
28.
Now,
7,
now,
0.
now. Time's up.
Are you lying to me?
I know you feel like I'm lying to you, but now you're going to know I'm not lying to you. The answer is... Bad question.
What?
19 is not a member of our set.
Does it need to be?
Yes, it's an operation on the set.
Oh,
You have to take 2 things out of your set and apply the operation to it. So, be careful. Here's our set. It's like when we were trying to apply divisible to pi. Pi is not an integer, we define divisible on the integers.
that's what you did.
Modular arithmetic is defined on some set that we take it from.
Okay.
Here it is in this case. And so, bad question. Not 8. Okay, what's 5 times 5?
5.
5 times 5 is 25. The remainder, when you divide by 10, gets us back to 5. Alright, what's 5 times 8? 5 times 8.
Yeah, it's 0.
40 mod 10 gets us to 0. 2 times 2?
4.
2 times 2?
4.
2 times 2?
4.
Just 4. Okay?
Okay.
Just making sure you can do 2 times 2. Okay, 9 times 8?
6.
No, it's 2.
No.
It's 2.
It is 2.
It's 2.
It's 2. 9 times 8 is 72 mod 10. The remainder would be 2. What's 9 times 9? 1. Last one, what's 10 times 10?
Bad question.
Bad question. 10's not in there.
Goodness.
Alright, you fell for it again.
I did.
Okay, so now let's do Z13. And repeat. So this now includes
11, 12.
10, 11, 12. Okay, so there's our set. Once again, let's repeat and see what all our answers come out.
Well, are gonna be the same. No.
No, they're definitely not going to be the same.
Not the same.
Some of them will happen to be the same, but what's 5 plus 5?
10.
Mod 13. Still 10, doesn't change anything. Okay. 5 plus 8?
4. 1.
0.
0. 5 plus 8 is 13.
Oh.
Mod 13 is 0. 2 plus 2?
4.
Still 4. 9 plus 19?
Still not bad.
Still a bad question. 5 times 5? 5 times 5?
12.
How many times does 13 go into 25? Once, with the remainder of 12. 5 times 8?
1.
1. 5 times 8 is 40. 13 goes to 39. 13 times 3 is 39. 2 times 2?
4.
4. 9 times 8?
11.
12.
What's the quotient? How many times does 13 go into 72?
That's
It goes in 4 times, right?
What's 13 times 4?
52.
52. Can you fit another one before you get to 70?
Yeah.
2. 52 plus 13 is
65.
65. How many more do you need to get to 72?
7.
7.
I was a little off.
Come on, you guys. 9 times 8. You should be able to do this. All right. 9 times 9?
81.
Does that just go evenly?
There's no way I do this right. Does 13 divide anyone?
With a remainder. Can you guess what the remainder is?
I'm not sure.
None of you are doing what my kids usually do,
Which is what?
which is not rethink about it from scratch.
I tried that, but I got lost.
Um,
You know, 9 times 8 is 7, then 9 times 9.
how many more 9s is this than this?
1 more 9.
One more 9. What's 7 plus 9?
16.
Mod 13 is
3.
3.
That makes sense.
Right?
Yeah.
You know, just keep counting your 9s. You start with 9. Plus 9 gets you to 18, but mod 3, that's a 5. Plus 9 is 14, which gets you 1. Plus 9 is 10. Plus 9 is etc. If you want to think about it that way. So, most kids usually think to add 9 and go forward there. Or at least all my classes, there's usually one kid who sees that.
Yeah.
You guys are a disappointment. All right, 10 times 10.
9.
9.
Mod 13.
Let's see, multiples of 13.
I don't know.
13 times 7
That's the
is
worst
91.
number to do for this.
13 times
That's why you
7
use
is
it.
91, right?
13 times 7.
91.
Yes. So it's 9? Your remainder is 9?
Just 9. Okay. There we go. Modular arithmetic. Way easier, right? Because you only have a few numbers you have to worry about. You already guaranteed your answer is just one of 13 numbers. Right? You don't have to find one out of infinitely many possible numbers. Okay.
Yeah.
So, one of your homework problems is going to be to show that if A and B are in Zn, then A plus B is also in Z sub n, and A times B is also in Z sub n.
So it's closed?
So it's closed on those operations.
Oh,
It's
wait.
impossible for them to output a number not in Z sub n. Now, this almost makes perfect sense. When we add them together, we mod by
Size.
n.
Yeah.
Mod gives you the
Remainder?
remainder, and the remainder always has to be less than what you're dividing by. So the remainder always has to be less than whatever your n is. So it always has to be less than what you're dividing by. So your remainder always has to be between 0 and 1 less than that. And what exactly is z sub n? It's 0 all the way to 1 less than that. So there's a scratch outline of basically the whole proof. Okay. Some properties that we have in modular arithmetic. Same properties that we have in standard arithmetic. A plus b is the same thing as b plus a. A times b is the same thing as b times a. Or in other words, these operations are commutative. And then a plus b plus c is the same thing as a plus b plus c. And same with the multiplication, or in other words, they're associative. And a plus 0 is always equal to a, or in other words, 0 is your additive identity. And a times 1 is always equal to a, or in other words, 1 is your multiplicative identity. And then finally, your distribution rule. Let me just say, for those of you who have already, we did a little bit of group theory and logic. This is a very standard example of a group doing something like z sub 10 and plus. That would be a group.
Gotcha.
It's going to be associative, it's going to have the identity element, and we didn't do the inverse part yet, so I guess you can't see that just from this, but common example for a group is using this modular addition. Okay. Move the camera. Let's go over one of your guys' homework problems that you guys already did, since you all did your homework. I'm very impressed by that, by the way. Blew my mind.
Thank you.
I can't tell if I can see it all. Okay, that barely fits it all. Okay. So, from your homework, you were asked to prove that if A is congruent to B mod n, prove A is congruent to B mod n if and only if A mod n is equal to B mod n. So, this is your homework problem. Let's go over how to do that exact homework problem because it's very useful for the remainder of number theory. So, forward direction. I'm going to show that if this is true, this is true. Good? Alright, so start out with let A be congruent to B mod n. What does it mean for A to be congruent to B mod n? N divides their difference. So then n divides their difference. What does it mean for n to divide their difference? N times some integer is equal to their difference. Good so far?
Yeah.
Pretty straightforward, just unraveling definitions. Okay. Now, A mod n, what is that equal to? Well, what is A? Maybe you should have written one more step here. That might be just a little bit of a leap. A is equal to n times k plus b. Good?
Yeah.
Okay, so now I'm trying to show that A mod n is equal to B mod n. Alright, so A mod n is equal to A mod n. Now, maybe I'm doing too much of a leap. I don't know, maybe you can see it. N times k mod n is always and forever. Let's say that I'm doing mod 10. What is 10 mod 10 equal to? Huh? 0. Oh, but what if we do 2 10s? Now what is it? 0. What if we do 3 10s? 3 10s mod 10 is 0. Okay, well, what if instead of having a 10 here, I do a 9 and a 9? Still just 0. When I take some multiple of 9, and I divide it by 9, I'm always going to get exactly what that multiple was. And the remainder will always be 0. So n times k mod n is always and forever 0, because it's n and n there. Okay, so this is just going to be whatever b mod n was. Because nk goes to 0. So a mod n is equal to b mod n. And we're done. That's what we were trying to show. Okay, now let's go the other way. I'm going to show that if a mod n is equal to b mod n, then a is congruent to b mod n.
Okay.
Alright, so assume a mod n is equal to b mod n. What is a mod n? Always keep this in your head. It's the
R word.
It's the remainder when you divide. So if I know, if I have a mod n is equal to b mod n, I know that there must exist two integers, two quotients. So I'm going to look at a divided by n and b divided by n. There has to be two integers, two quotients, such that a is equal to q1, whatever that quotient happens to be, n, plus the remainder, and b has to be equal to some quotient of n plus the remainder. Now, how do I know that these are the same r?
Because a mod n is equal to b mod n.
Yeah, because a mod n, or in other words, the remainder when you divide by n is equal to the remainder when you divide by n. Here's me dividing by n, here's me dividing by n. Their remainders have to be equal. That's what this is saying. Their quotients may be the same, may be different, but their remainders are for sure equal. And now, I'm trying to prove a is congruent to b mod n. I'm going this direction. So I need to show that a minus b is divisible by n. So what is a minus b? Just flat out plug in. Here's a. We're doing minus b, so you gotta make both numbers negative. Positive r minus r is 0. So those go out, so we're left with just these two terms. Factor the n out. So a minus b is equal to n times some integer.
The question was
So n divides a minus b, or in other words, a is congruent to b mod n. So there was your homework problem.
Cool.
Okay, so now, just to give you the sense for proving one of these, I'm going to prove associativity right here. Okay. And for these types of proofs, it's often helpful to go back and forth between thinking about it this way and thinking about it this way. So that's why we did that little proof first. Okay. So let n be any positive integers, and let a, b, and z sub n. We're going to prove that a plus b plus c is equal to a plus b plus c. Okay. Now, I'm going to write this out once, and from here on out, I'm going to do this in one step. I'm going to go from this to this. B plus c, using modular arithmetic, is always the same as b plus c plus some integer number of n's. I'm going to show that out once. Probably should have made this its own little lemma. And it's just something that we're going to use over and over again. I'm going to be okay with you making this leap.
Okay.
All right, but let's write it out just to see it once. So what is b plus c? By definition, that's b plus c mod n. Okay? Now, when I do my quotient, I'm guaranteed that there exists unique q and r, such that for b plus c, I'm dividing it by n. So we're doing a number mod n, so same thing as we did before. So I'm doing b plus c divided by n, gives me some number of n's plus a remainder. Good?
Yep.
Okay. So then b plus c mod n is equal to b plus c plus, well, did I lose you in this? What is this equal to? Did you follow what this is equal to?
That's the remainder of your.
It's equal to our remainder,
Yeah.
which is what this gives you. The remainder. So, follow this one more time. B plus C mod n is equal to our remainder. But our remainder, just substituting in, is equal to that.
Yeah.
Call negative q k.
Okay.
So my only point there is b plus c, using modular arithmetic, is always b plus c plus some integer number of n's, using regular arithmetic.
Okay.
Let me give you a concrete case of this just to be very clear. Let's go back and say that we're in z sub 10 just to keep it simple for us. And let's look at 9 plus 9. What is that equal to?
18 mod n.
Yeah.
It's equal to 18 mod n, which is also equal to just 8. Notice that 9 plus 9 is always equal to 9 plus 9 plus some integer number of tens. In this case, negative 1 tens. Okay, so that's all we're saying there, and that is a substitution you can use over and over again. B plus C in modular arithmetic is b plus c plus some integer number of n's in regular arithmetic. Good? Okay, so with that little side note, now let's get started with the proof. What is a plus b plus c? Well, just plugging in the definitions, that's a plus whatever this is, mod n, and what's the inside? That's b plus c mod n. So just plugging in the definitions. We're doing that one first, followed by this one.
Yeah.
With me?
Yeah.
And what is b plus c mod n? Well, that's b plus c plus some integer number of n's.
Yeah.
And what's a plus an integer mod n? Well, it's just going to be the sum of all those plus some integer number of n's. Whatever k1 and k2 are, add them together, we're going to call it just k. So a plus b plus c is equal to a plus b plus c plus some integer number of n's. See that? Okay.
You just gotta group it and then, like, is that what we're trying to do?
I'll just keep going. And then just tell me if something's not making sense.
Mm-hmm.
Okay, so then I have a plus b plus c plus some k number of n's is going to be congruent to a plus b plus c mod n. How do I know that this is true? What's their difference? What's this minus this? Just some integer number of n's. So this is true. This is the exact same as that. So notice that a plus in modular arithmetic, b plus c, is equal to a plus b plus c mod n. We could do the exact same thing for this. If we were to expand this all out, then it would have been a plus b plus c plus some integer number of n's. And so it is going to be also congruent to a plus b plus c mod n. So I didn't bother writing it out for this, but it would be the same two steps. You say that was, or sorry, you start with, where did we start? That would have been equal to something similar to that, and then using the same logic again. You good? So the point is, this is congruent to a plus b plus c mod n, and this is congruent to a plus b plus c mod n. Which means, so I have these two are congruent to each other, mod n. Maybe that's just using a transitivity and reflexive, but then using this, so that's going from here to here. What does this one say?
Isn't it saying the same thing?
If they're congruent to each other, mod n, then the first one, mod n, is equal to the second one, mod n. So since these are congruent to each other, mod n, then the first one, mod n, is equal to the second one, mod n.
Oh, yeah. Oh.
But modular arithmetic, mod n again, doesn't change it. Modular arithmetic, mod n again, doesn't change it. Once you have the remainder, dividing it by n again doesn't change the remainder.
Yeah. Shit.
Okay, so there we go. There's that. Now we want to introduce subtraction. How do we do subtraction with these things? So far we've done addition, so far we've done multiplication. Let's introduce subtraction. Now, in arithmetic, when we cover arithmetic, the only operations that are given to you are plus and multiplication. And then you define subtraction and division in terms of plus and multiplication. So, when you did arithmetic, just regular arithmetic that you know and love, then you would have had a definition something like this. So in arithmetic, we define a minus b to be the unique x such that a is equal to b plus x. In other words, we define it so that a minus b is equal to the thing that I'd have to add to b to get a. Just in time.
Right?
We just started.
Oh my gosh, that is so much.
Alright, so let's see a concrete example of this. What is 8 minus 3 equal to? 5. And if you had to prove that, how would you prove that that's the case? Well, that's because 5 plus 3 is equal to 8. That's how you validate it. What is a minus b? It's the unique number you'd have to add to b to get back to a. What's 5 minus 3? It's the unique number you'd have to add back to 3 to get to...
Yeah, you said
I think I said something wrong. What's 8 minus 3? It's the unique number. You'd have to add to 3 to get back to 8.
Yeah, that's what you said.
Ah, feels like I said something weird. Okay, so now we want something similar for modular arithmetic. Intuitively, let's go back to saying we're in Z10. Or let's start with on the clock. If it's 1 o'clock, then 3 hours ago it was 10, right? And so,
Oh, yeah.
if we were in Z sub 12, then you would expect, I can't even remember what I just really said now. I think I did 10. I said 10 minus 3 was equal to,
1 minus 3
1 minus 3 is equal to 10.
oh, thank you. 1 minus 3 we would expect to be equal to 10 in Z12.
I think you wrote that wrong.
1 minus 3.
I keep saying one thing.
Don't worry, that will be erased.
1 minus 3 is equal to 10.
Okay.
Right? 1 o'clock, 3 hours ago, it was 10 o'clock. Goes backwards around the circle. That's what we want to define subtraction to act like.
Is that what you've been talking about? Like, that's all it is?
No.
Now,
No, that was something else.
that's a lot of other stuff. Sorry. I could try and summarize it for you, but it'd probably take me like an hour and a half.
Why is it so long?
Because it's a lot of material. Okay, anyways, so we need something similar now for modular arithmetic. So let A and B be in Z sub n, whatever that is. We are going to prove that there exists a unique x in Z sub n, such that A is equal to B plus x. And that x is ultimately what we're going to mean by A minus B. Same exact thinking we had up here. So first I need to prove that there is such an x, and then once I prove that there is such an x, then we will define subtraction. Here's how we're going to ultimately define subtraction. Let A and B be in Z sub n, then A minus B is the unique x in Z sub n, such that A is equal to B plus x. So this will be our definition. This proof is first proving that there is such an x. Good? Okay, so let's prove that there is such an x. So let A and B in Z sub n, we're proving that, oh, sorry. So here's our first line. What is the x here? How did you come up with the 10 here?
It's a number you had to add 3 to 1.
You just did 1 minus 3, which is negative 2,
Yeah.
mod 12.
Okay. Okay.
What is negative 2 mod 12? How many times does 12 go into negative 2?
0.
No.
What?
Otherwise the remainder would be negative 2.
You can
It's always one less than what you want to say. You want to say 0, so it's
Negative.
negative 1. And you want to say that the remainder is negative 2, so the remainder is 10.
Yeah.
Alright? That's how you came up with this. So we're going to say, right out the door, let x equal a minus b mod n. I'm going to prove that x is what we were trying to get at with this minus symbol. So same way that you calculate that 10. How did you get that 10? You did that minus that, mod, whatever you were in. You did a minus b mod, whatever the n is.
Yeah.
So let x be a minus b mod n. My job is to prove x satisfies this thing.
Yeah.
Now, right out the door, what does that mean? That means that there exists a unique q such that a minus b is q n plus x. X is the remainder when I do a minus b and I divide by n. That's what x is. So here's a minus b divided by n with the remainder x. What do I know about x?
That's equal to
Since this is a remainder, what do you know about your remainder?
It's less than your n.
It has to be smaller than your n, and it has to be greater than or equal to 0. So my x has to be smaller than n and greater than or equal to 0. That's exactly what z sub n is.
Yes.
It's 0, 1, 2, 3, da, 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 all the integers between 0 and n, not including n. So x has to be in z sub n. So far I showed this x is in z sub n, so it satisfies one of these conditions. Now I need to show that it's equal to this, and then I need to show it's the only thing equal to that. So far I showed it's in the set.
Yeah.
Okay, now let's calculate b plus x and see if we get a.
Okay.
So then, what's b plus x? Well, that's b plus x. How did I calculate my x there? Just from this.
Okay.
Sorry, probably should have written that as a separate line. Just move the qn on the other side, makes it negative.
Yeah.
And that gives you your x. So b plus x is b plus x, mod n. Just find the definition. When you mod n, do the algebra first now. Now we have a b and a negative b. Those go out. So I'm left with just a minus qn, mod n.
Okay.
When I take any integer multiple of n and I multiply n, I get 0. So I'm left with a mod n. But a is already in z sub n. So a mod n is just a. Follow that?
Yeah.
Okay, so I proved that this x, in fact, does satisfy this piece now. I showed that b plus x is in fact a. Now the last thing I need to show is that x is unique. It's the only answer. Why is uniqueness so important? We want there to be one and only one answer. I don't want 13 minus 7 to have more than one answer, otherwise I can't figure out what 13 minus 7 is.
Right.
I don't want 13 minus 7 in whatever system we're in to have more than one answer, otherwise
You can't figure it
it's not well defined. If you remember going back to logic, when we talked about theory or definition being well defined.
Yeah.
One of the properties it has to have is that uniqueness property. So we want it to be well defined. So now, assume by way of contradiction that there exists some y, such that y also gives you a when you add it to b, and y is something different from x. So assume that there's something else out there that satisfies this. I'm going to prove that it is in fact the same thing as x. Contradiction. Therefore, there is no y. Okay. But I know that b plus x is equal to b plus x plus some integer number of n's. Told you we're going to be making that leap a lot. That's what we did starting here, going to here. That's a leap you can go ahead and start making now. So, lost my place. Right here. B plus x is equal to b plus x plus some integer number of n's. B plus y is equal to b plus y plus some integer number of n's.
Yep.
Okay. Now, a is equal to b plus x plus this. Because I already know a is equal to b plus x. That is equal to that. We already showed that somewhere. Right here. B plus x is equal to a. And we're assuming that b plus y is also equal to a, where y is something different. So I know a is equal to this, and a is equal to that.
Yep.
A is equal to b plus x, a is equal to b plus y in modular arithmetic.
Yeah.
Okay, so if this is equal to a and this is equal to a, then what do I know?
They're equal to each other.
Oh, that's not what I was going to do.
Oh.
Sorry. I'm just going to solve this one now for x and this one for y, and show that they're the same number.
Oh, okay.
So solve for x, solve for y. Okay. How am I going to show that they're the same number? Once again, I'm going to use this thinking, going from this to this. So I'm going to show this holds form, therefore this holds form. So, what is x minus y then? I solved for x, I solved for y. What's x minus y equal to? I'm going to show it some integer number of n's. Here's x. And now I'm going to subtract y. So that becomes negative, that becomes positive, that becomes positive.
So
A's and B's go out, and I'm left with k2 minus k1, or negative k1 plus k2 if you want to think about that, times n. Which gives me x is congruent to y mod n, which gives me x mod n is equal to y mod n. But since we're assuming x and y are both in z sub n, then x mod n is already just x, and y mod n is already just y. So that gives me x is equal to y. Contradiction. Therefore, x is unique. And now we proved it's unique, we can now define subtraction. So let a be in z sub n, then a minus b is a unique x in z sub n, such that a is equal to b plus x. Exactly the same thinking we were using up here. Now that isn't how we want to compute it. We want to compute it this way. When I say what is 13 minus 7, what system should we be in? We'll say mod 4. No, it has to include 13.
Mod 14.
So mod 14, we'll go ahead and say mod 14. It's more interesting if we go the other way. Let's look at 7 minus 13. and pretend that we're in Z14. What's 7 minus 13?
It's -6.
Negative 6, and then mod 14 gets us
Positive 8.
positive 8. So the way that you calculated that is you did 7 minus 13 mod whatever we were in this case 14, right? So I'm going to prove that this is in fact equal to that, and this is a valid way to calculate it. You don't have to go searching for the x, you can add the b to get a, you can just calculate it that way. That's what this quick proof is going to be.
Okay.
So let a and b is en, then a minus b is the exact same thing as a minus b mod n, and you can calculate it the way you know and love. That's how we're going to prove here.
Okay.
So let x equal a minus b mod n, then x is equal to a minus b plus some integer number of n's, right? And x has to be in z sub n. So x is in z sub n because we're modding by n, and here's what it's equal to. So then b plus x is going to be equal to, and we're going to show it's equal to a. Therefore, this x is the valid x. So b plus x is equal to b plus x mod n is equal to, notice b's go out, and then some integer number of n's mod n is always and forever
There's the
0, so it just leaves you with a mod n is a. So yes, when I make x equal to a minus b mod n, it is a solution to that. So that is a valid way always and forever to calculate the one and only x. Therefore, a minus b is equal to x. Okay, so let's just end with a few examples and then we're done. So that doesn't end the section. We still have to do division. Division is a pain.
Division sound like everything.
Why?
Why is division going to be a pain? Let's imagine, let me stay on the board. Let's imagine we kept going with the exact same process and you tried to define it the way you know you want to define it, right? So, what would happen if I did, let's say that we're in Z sub 10, and I decided that I was going to do something like 4 divided by 2, whatever that was equal to. With me so far? Now what should that be? That should be the number such that when I multiply it by 2, I get 4.
Why do you circle this one?
Because it's modular arithmetic, not arithmetic. All the way back to our definition over here.
Okay, I'm sorry. Are people just adding stuff to math to make them sound smarter? Because that literally does nothing. It does nothing. You
It's-
put a circle around
It's
it.
exactly what you do when you keep track of the minutes. I tell you that it is 11 but 55 minutes. So it's 11:55. Okay? I ask you, what will a minute show in 10 minutes?
What?
So it's 11:55. We'll say in 10 minutes what time will it be.
Oh.
And the minutes will show 05, or in other words 5. You added 10 and you got around to 5. Because it just circles around.
Oh, okay. That makes more sense.
That's all we're doing when we do this addition. Now, why doesn't this work? So, if 4 divided by 2 is equal to x, then x has to be the thing such that x times 2 equals 4, right? Okay, so let's see. What is the thing that gives you 4?
Or D sub 10?
We're in Z sub 10.
Are there multiple solutions?
Yeah, so 2 does. 2 times 2 equals 4, so that one works.
But there's more than just that.
But what else is there?
7.
7. 7 times 2
Oh, yeah.
is also equal to 4. So what's the answer? Is it 2 or is it 7? You might have a bias towards 2 in this particular situation, but the point is it doesn't work.
Doesn't work. Interesting.
And so we're going to find out that the only time it does work is when the two numbers we're talking about are relatively prime. Their GCD has to be 1 in order for it to have an inverse in the system, which is where that theorem I told you is the second most important theorem is going to keep coming up.
Okay.
So division's hard. So we'll deal with division next week, but for today, let's just do some subtraction now.
Sweet.
So here we are in Z sub 7. What's 5 minus 2?
3.
3. What's 2 minus 5?
1, 7, 4. Wait. 9.
2 minus 5 is, can't get 9.
So annoying.
2 minus 5 is
-3.
negative 3. Remember, when you're in z sub 7, adding 7 never changes your answer.
Yeah.
Adding multiples of n never changes your answer. In other words, this would give us negative 3 plus 7 is 4. Alright, what's 6 minus 4?
It's 2.
Just 2. So subtracting is always easy when it's a bigger minus a smaller. What's 0 minus 2?
It's just 5.
We're in mod 7, so negative 2 mod 7 is 5.
Sweet.
Okay, so that's how you do subtraction. So you now know how to add, multiply, and subtract. Alright, that's it for lecture. Nice short one for you. Now we're in 35 minutes.